Welcome to the session on friction factors as part of the NPTEL MOOC on transport phenomena and materials. So, in this session we will be looking at the definition of friction factor. The friction factors go by names of different ways of modeling them, and we will be taking up what is generally the default one handled in many of the metallurgical textbooks. We will take 4 problems and then derive the friction factor expression for these. The analytical solution for the velocity for these 4 problems has already been covered in this MOOC. See, the definition is as follows. Friction factor is this quantity f that we have written here, and it is defined as the expression here f, capital F, which is a force, is equal to small f into area A into k, which is the kinetic energy per unit volume. Okay. So, if you see this k and if you multiply with the volume, then you get the kinetic energy half mv square. Now, from this definition we can already see that there is a meaning for this f, and we will come to that interpretation in a moment. The force is generally to be modeled as follows. It is to be taken as the pressure drop that is across the domain that is causing the flow into the area over which it is acting. So, which means that it is normally the cross sectional area. Okay. And this is not the same area as A that is written here, because that is modeled in 2 different ways for 2 types of problems. So, what are called as the internal flow, for example, the pipe flow is an internal flow where the wall is in the surroundings, and so such problems we take the wetted area. So, here the wetted area in the case of pipe flow would be, for example, the perimeter times the length, that is pi d L. Now, in the case of external flow, that is the flow over objects, like for example flow around a sphere, then we take the projected area. So, projected area in the case of flow over a sphere would be, for example, the cross sectional area of the sphere itself, which basically is pi r square. So, you do have, for example, different ways of defining A, and so we need to watch out which type of flow we are looking at, and accordingly take that expression. Okay. And the u is again the velocity that is taken representative. So, very often it is the average velocity that we are considering. So, here the interpretation, the meaning of this friction factor f. So, here if you see the way we have written the expression, it is basically seeing that how we are able to convert the pressure that is applied over the cross section into the kinetic energy of the liquid that is flowing through. So, it is basically the efficiency by which we are able to convert the driving force for flow into the actual flow itself. Okay. And when a friction factor is taking a very small value, it actually implies, if you can see this expression, this is small, it implies that if this is remaining constant, then you would require less force to achieve the same amount of kinetic energy, which means that getting to flow regimes in which friction factor is small would be good, because that would be more efficient. And we have to also look at the definition of a friction factor that is different in different models, but by and large we can say that when nothing is told, then it is this way that we are considering the friction factor. Okay. So, some of the applications of friction factor, why do we need this concept at all? So, we have already seen that we have the analytical solution for the velocity. So, if you have u, and you already have u as a function of r, u as a function of r and theta, u as a function of y, and so on. So, usually these are all basically spatial variations that are available, and very often the spatial variation is not relevant. For example, in situations like in turbulent regime, the spatial variation is actually a function of time, and there is no point in, for example, describing elaborately what would be only a transient in nature. So, it would be good, for example, if we can take what would be time averaged velocity over the entire domain and see how that magnitude of the flow can be determined. So, the correlation for such magnitudes of flows can be derived for analytical flows that we have already. So, we will be doing that, but we can use the same model to extend such correlations into turbulent regime. So, in other words, you can say that we actually use friction factor where we are interested in the magnitude of flow, but not necessarily the variation of the flow. Okay. So, you cannot, for example, get the spatial variation of flow if you take the approach of friction factor the way we are describing here, and we are also then conscious that it provides a means to extend what we have learnt, our expressions, extend our results from the analytical solutions to turbulent regime. Okay. That is because then we are actually having some way by which we can use those expressions for some industrially useful problems. And we do have, for example, situations where there are geometrical complexities. For example, there is a pipe flow problem, the pipe is actually not of exactly circular in cross section. So, then what do we do? So, we need some way by which we can handle that deviation as how it is affecting the pressure drop in our problem. So, we need a means, and here again we are having that possible because we can handle that. For example, the pipe may not be smooth, it may be rough inside because of corrosion, and how does that affect the pressure drop? So, we will have those things handled, because once we have a way to have the correlation of friction factor, then we can add more terms to it as the industrial situation demands. And we also have situations where assumptions can be also deviated and given as a correction factor. For example, the pipe is actually straight line and we are actually saying strictly axial flow in the Poiseuille flow problem we have discussed earlier. Now, for example, the pipe is exactly not straight, but it has some bends. So, each of the bends will involve some amount of change in the efficiency of the flow that will be taking place, because there are these gradients that are taking place. So, the horizontal velocity has to come to a stop and the vertical velocity has to start. So, those gradients are all going to dissipate the energy, and therefore, some way by which each of these bends, because of the theta angle bend, should lead to some pressure drops. Now, how are we going to get these? So, these also can be modeled using the concept of friction factor. So, that way this concept is very useful in handling the real life problems, and we would then see how these expressions look like. So, the first problem is reuse of the pipe flow problem that we have done earlier, and we have already seen that the pipe flow problem where we are looking at the axial velocity because of a pressure drop per unit length that is taking place. Okay. And you see that such a flow is already modeled by us, and here is the result for the average velocity. The velocity expression itself is given as parabolic, that we have already come across, and we have seen that this kind of a result is applicable when the Reynolds number is less than 2100. So, the whole idea is what do we do about that number. So, that is where we are actually headed, and let us see for the range that is valid, how does the friction factor appear using the method that we have seen. So, what we do basically is look at the terms that we have taken up. So, the pressure is delta P, over which the domain entire domain is actually experiencing the driving force for flow into the area over which, cross sectional area over which the delta P is acting. So, that becomes the force term, and the solution of the average velocity is already given here, and that if you simplify, then what we can do is eliminate. So, you can eliminate delta P between these two expressions. So, when you eliminate, then what happens is that you can get what is the F. So, F is, this is F, but you can eliminate delta P using this expression. So, when you substitute that, you will get the expression for F. And then the wetted area. So, we know that the wetted area is nothing but the perimeter into the length, and that is given here, and the kinetic energy per unit volume is here. So, once we have all these expressions, then we substitute these. So, we put the term here and the wetted area here and the kinetic energy per unit volume here. So, immediately we will get what would be the friction factor. Interestingly, once you evaluate, you would get the friction factor to be like 16 mu by rho du, and immediately you can see that in the denominator there is a Reynolds number that is sticking. So, which means that you actually have the friction factor is coming as a function of Reynolds number, and this was actually the design behind the formula that we have actually decided. Okay. And once we have this, then we would see how very interestingly similar kind of forms will come in other problems also. Usually we can see from the units that the friction factor should not have any units at all, it is a non-dimensional quantity. So, it must be also a function of only non-dimensional quantities. You normally do not encounter friction factors as a function of, for example, length or diameter, etc. They must always be normalized with quantities of similar dimensions, so that you basically have non-dimensional quantities. And very often in many of the problems, it is a function of only the Reynolds number. Okay, so for the Reynolds number less than 2100, the friction factor is given. Okay, now we can then use the same approach, that is in a given experimental problem, we can actually measure what pressure drop is causing what kind of a velocity, and make a correlation and then get F, and make the correlation with Reynolds number as the regression variable, and then see how the friction factor should evaluate. And that actually is given in many open literatures that are available, and there are some results that are actually for a very wide range of Reynolds numbers, and therefore they are also very popular. So this relationship, for example, is applicable for turbulent regime, and it goes by the name Blasius equation, and the friction factor is then given as a power of Reynolds number to raise to minus 0.25. Normally you would see that here, for example, friction factor is going as Reynolds number raised to the power of minus 1. So you would see that the power here, this quantity generally is small. Okay, if you look at the magnitude, small for the turbulent regime, and it is large for a laminar regime, which means basically that once you have these expressions, you can already make a guess which expression could be for what kind of a regime. But nevertheless, you must always look up the exact range of Reynolds numbers over which such a correlation has been fitted. So please remember that this is empirical, okay, which means that it has been derived from experiments, and this is basically theoretical, because it has been derived from analytical expressions. It turns out that, of course, this is also valid for experimentally similar problems over the wide range of Reynolds number up to 2100, but nevertheless we must know the origin. So there are things that are from theory, and there are things that are from experiments. Now the problem of deviation from assumptions, we have assumed in the pipe flow that it is a smooth, rigid, straight pipe, and in case it is not smooth, if there is a roughness that has been developed inside because of the corrosion, etc., then what do we do? So we then define this zeta variable, which is basically called as a relative roughness. So relative roughness is basically defined as the roughness itself, which is basically delta H divided by the diameter. Delta H is basically usually RMS value, that is root mean square value. So if you look at a pipe and inspect the region which is the inner surface, then that region would appear to be rough like that. And this profile, if you then were to see what is the root mean square value, so this delta H is what is given as roughness. In other words, roughness is nothing but in length units, and you can say roughness of 50 microns, roughness of half an mm, roughness of 1 micron, etc. And if you divide it by the diameter, we get the relative roughness. So this is relative roughness. So it is basically non-dimensional. Okay. So we have basically the friction factor made as a correlation for not only the Reynolds number, but also the relative roughness, which means that even for rough pipes, we do have a way by which we can go ahead and evaluate what would be the pressure drop required if you want to push fluid through it at a particular velocity. And for the velocity, you evaluate the Reynolds number and then plug it in with the roughness, and you get the friction factor. That would give you what would the delta P look like, etc. So like this, we can actually solve real life problems by using these kind of correlations. And when we plot these three friction factors over a complete range of Reynolds number, we see something interesting. We plot it using log plot. Okay, so you notice here that it is log, okay, and the log plot. So remember that it is always made a log plot, and the log plot of a function that looks like f is equal to something by Re would naturally have a negative slope of 1, which is 45 degrees in the negative way, which you can already see that is visible here. Okay, so this region is coming from this expression, okay, and this region is coming from this expression. Okay. So, you could see that in the left hand side of the log plot of friction factor as a function of Reynolds number, you would have basically a straight line for the laminar or analytical derived friction factor, and you would have a fairly flat region. So, you could actually see that straight line drooping downwards and fairly flat region for laminar and turbulent regimes respectively. Okay, so, we will see whether this kind of a trend is replicated in other kind of domains or so. Okay, so, we will see that, and that would be something as a learning as we go along. So, I am actually showing you how to plot multiple functions in different regimes in a mathematical notebook by taking a screenshot here. So, the strategy to solve numerical problems once you have these correlations is as follows. Basically, upfront once we have a problem where the pressure drop required is to be determined, and then we do not know, for example, whether the flow is in laminar regime or turbulent regime. So, we do not know. So, upfront what we normally do is look at the diameter of the pipe, and if it is large, okay, it is large in the sense centimeters or more, then maybe it would be turbulent, and go ahead and start with the turbulent regime expression. So, in other words, we have to basically assume. So, we have to basically assume the regime of the Reynolds number and pick the friction factor from that. Once you pick the friction factor expression, which means that then you could use it to solve for the velocity. So, the velocity solution would then require, for example, some iteration depending upon the complexity of the expression. For example, if you take the rough pipe expression, you do have the logarithm term. So, there will be some iteration that is required, and usually if you use a software like MATLAB or Mathematica, you can directly solve for it. Otherwise, you could also use a calculator and use what is called single point iteration scheme, and then get this kind of a solution. So, we would have some practice of such problems in tutorial anyway, but once you solve for the velocity, without forgetting, we should always evaluate what would be the Reynolds number and see that the Reynolds number that is coming out is in the range that we have picked. Okay. So, if it does not fit in the same range, if it is not in the valid range of the Reynolds number, then what we have to do is that immediately change the expression to another range depending upon what range we have got. So, to just illustrate that point, let me tell you here. You see that if you assume this problem and you get the range that is actually very small, which is less than 4 into 10 to the power of 4, then you go to the other expression here. So, like that you basically change the expression so that you can pick the correct friction factor, and then we can again repeat the same scheme. So, usually you would converge to one of the regimes as long as the problem is well defined, and once you converge, then what happens is that the Reynolds number you get would be in the same range as you have started for the friction factor, and then you can just see that the velocity that you got is actually valid, and then you can say that the problem is solved. So, one needs actually an intelligent guess to pick the correct range for a solution, but even if you get it wrong, it does not matter, because as you keep going through this cycle, you would be actually coming closer and closer to the correct solution. So, now let us move on to a problem which we have solved earlier, the flow over a sphere, and as you have seen, it is a very tedious derivation, but in the end we will see how the final velocity, terminal velocity, can then be used for correlations. So, here is a situation, you have got a sphere and you have got the flow that is going around, okay, and this far field velocity is u, which sometimes we write u infinity or so, terminal velocity, and in case the solid is actually falling down and liquid is stationary, then you call it terminal velocity, but the problem would still be same, namely flow over a sphere. And this is in the creeping regime. The analytical derivation we have done is for the creeping regime, which means that the Reynolds number, critical Reynolds number is very small, so 0.1. So, for extremely small values of Reynolds number only you can use this. Now, the way we have derived the Stokes law, we have already done the integration of the pressures and stresses that are acting on the sphere and arrived at the force. So, we directly can use a force, we do not have to do any more manipulations there. And because the flow is external, we would be using the projected area, so that gives you pi r square, and then the kinetic per unit volume is already there, kinetic energy per unit volume. So, you then substitute those, and then you would go for the F. So, F is available here. So, you can see immediately that F is coming very similar to the expression which we have derived in pipe flow. There it is 16 by Re and here it is 24 by Re. Okay, so, which means that the way we are going about derivation seems to be fairly universal in its application. And we can then see how friction factor was modeled in an experimental correlations for the rest of the Reynolds number regimes. So, this is a laminar or actually strictly speaking it is creeping regime, creeping flow regime, and these are basically in turbulent regime. So, you could see that the friction factor expression is given in different manners in the different regimes. So, you could see that for intermediate range, that is basically for Reynolds number less than 6000, you are actually using an expression which seems to fit both the low Reynolds number regime as well as high, because at low you are actually having 24 by Re which is already repeating here, which means it is something like a hybrid function to span across a large Reynolds number range. And for intermediate you do have a more accurate function that is available, which is made from the regression. Okay. And as you can already see from the power that here is the power is -1, here is power is -0.6. So, as you go into the turbulent regimes, the power of Reynolds number for the regression that is done in empirical correlations generally tends to be small. And interestingly, it has been observed that at very high Reynolds numbers you do have the friction factor coming out independent of the Reynolds number. It comes out as a constant, and that also goes by Newton's law. There are a lot of things that go by Newton's name, and we must not confuse between these. So, friction factor being a constant is also observed in this domain. So, when we plot again all these things, you could see that they also follow the same trend. That is, you do have a straight line on the left hand side of the log plot of friction factor as a function of Reynolds number. So, the left extreme at very small Reynolds number you have basically a drooping down straight line plot, and as you go to high Reynolds number you have a flattened profile that is coming out. So, it is very similar to what we have seen in the pipe flow, and the functions which color is for what is given here. So, the first thing is red line. So, I write here there, and then you have got the blue guy. So, 0.44 is here, and the green line is here, the hybrid expression. Okay, so, hybrid expression is actually able to cover partly the flat region as well as the straight region, and you could see that the behavior is very similar, which means that when we do not know anything, then we can perhaps make some assumption on how the friction factor could be varying. The exact numbers we may not get it right because we need the correlations for it, but we can get the trend, and the trend is as follows. The trend is that when you take a log plot, when you take a log plot of a friction factor as a function of Reynolds number, then for very low Reynolds number, that is in laminar regime, you see that it is a function of 1 by Re. That numerator can be different for different problems depending on the geometry, but it will be a function of 1 by Re, which means that when you are going to take ratios and compare the relative values, then you do not need the constant in the numerator. So, you can go ahead and make this assumption and already come to some solutions of the problems. And at a high Reynolds number regime, which is turbulent, you could actually make an approximation that friction factor is constant. What value that would be is again something that we need from the experimental correlations, but we can make an assumption that it is a constant and make already use of such things for some problems. So, we will have few such problems already using these trends in the tutorial, and it is very good idea to have this particular image commit to our memory. That is, friction factor as a function of Re will be sloping downwards as 1 by Re and then becoming flat at very high Reynolds number. So, this image, if it is there in our mind, then there are many problems that can be solved directly to get the trends. Now, let us then see how we have modeled the porous medium flow. So, porous medium flow was modeled as a bundle of tubes. Okay, so, that is how you got the analytical solution here, which we gave a name, a Blake-Kozeny equation, and a bundle of tubes would mean that it is actually internal flow. Okay, so, this is important. the model that we have chosen is that it is an internal flow, which means that even though the porous body is made of spheres where actually the liquid is going outside of the sphere, it is still not treated as an external flow, it is treated as an internal flow because the void is being modeled as a pipe. Okay. So, that is exactly a mistake that many students make while applying these expressions. So, be watchful. The model is very important. To arrive at the expression, we thought of it as a tube, and therefore, it is an internal flow expression. And these expressions are valid for Reynolds number defined for the porous medium in this manner. That is the reason why there is a subscript that is given. So, Reynolds number less than 2 is where this particular expression is valid, and this is the expression. So, we have got delta p here connecting with the superficial velocity. Okay. And we are going to use superficial velocity only for all these porous medium approach, because we know that the actual velocity is of no relevance for us, because it is difficult to measure, and superficial velocity can be measured experimentally, and therefore, that is what we are going to use. So, when we say u in porous medium, that means it is superficial velocity, and the force term is nothing but delta p into the cross sectional area over which the pressure is being acted on, which we actually model as pi r square, because it is a tube, cross sectional area is pi r square, but for r we take the hydraulic radius. So, the expression for hydraulic radius is already available. So, we basically use this expression into that, and the delta p actually we eliminate using this expression. So, then we will get what would be the value of F, the force, and once that force is available, then we can then substitute it in here, and the wetted area is taken here for the area term, because it is actually an internal flow, and kinetic energy per unit volume, the u is basically same as us, which is superficial velocity. So, when you substitute all these things very beautifully, many of these things cancel out, and you would get basically the friction factor as 4.2 by REC. Okay. And this actually also is elegant, because the only constant that is sitting here is what is actually coming from the expression from the Blake-Kozeny equation, and then the functional form is again very similar to the other problems, namely 1 by Reynolds number. However, the Reynolds number is redefined for this particular problem using hydraulic radius and rest of the quantities as applicable. Okay. So, how does this expression then change when we go to other regimes? So, it is again seen here that friction factor is defined for less than 2 Reynolds number, but when you go to turbulent regimes, these are all turbulent regimes. So, this is basically creeping flow regime. So, for turbulent creeping flow or laminar regimes. So, for turbulent regimes you do have correction, and again like the Newton's law that we have seen for flow over a sphere, at very high Reynolds number we see that the friction factor turns out to be a constant. Okay. So, which again means that when we take a porous medium flow and it is told that the flow is turbulent, then we can just straight away take f as a constant and then go ahead and see how the pressure drops can be connected with the velocities. Okay. And when we plot these using a mathematical notebook, we will see that the three expressions are appearing to be the same. So, the log plot as a the friction factor as a function of Reynolds number is appearing to be a straight line drooping downwards on the left hand side for the low Reynolds number, and a flat region on the right hand side for the turbulent regime. So, you could see that the 0.292 is appearing here. So, 0.292 is here. So, you have got the hybrid expression that is here. So, the first expression, the linear expression is here, the hybrid expression is given here in between, and the expression for the turbulent regime is given here. So, you could see that the hybrid expression is reproducing the behavior at laminar regime quite well on the lower side, and the flat on the higher side quite well. So, this is a very useful expression here, 4.2 by r plus 0.292, and you could actually see that it behaves the same way as we have discussed earlier, which means that here it is basically slope downwards and a straight line, and you could see that here it is basically flat. Okay. So, when we do not know any expression about these things, then we define the friction factor the way we have seen earlier. So, when we write like this, then this behavior is already known. It is in a same fashion, namely straight line on the left hand side and flat on the right hand side. So, the expression for porous medium which is made of a bed of spheres is actually identical to the porous medium we have seen earlier, except for that the S naught is taken as 6 by dP. So, the reason being that when you assume that the spheres are all touching at point contact, then you can directly get the wettable area per unit volume of the solid analytically, and that comes as a 6 by dP, where dP is the diameter of the spherical particle that is consisting in the bed. So, we have redefined then the Reynolds number to accommodate this. So, S naught is replaced, and then we have redefined the Reynolds number, and that is why the subscript is changed now, which is E. And so, which means that for a laminar regime, that is within 10, then you have an expression that is available. So, we have got 4.2 in the Blake-Kozeny equation. We multiply with 36 because the S naught is coming as a square. So, you see that 150 will come in there, and we basically eliminate delta P between these two, and the expression that comes in you substitute in F, and then the wetted area is going there, and the kinetic energy per unit volume is going there, and when you substitute and cancel out terms, then you get the friction factor for flow through a porous bed of spheres as 150 by Re, which is very elegant because you can see that it is also similar to the other expression except for the factor of 36, and we already know where the 36 coming, it is coming from here. Okay. So, the friction factor expressions are given here. For the laminar regime, you do have them analytically derived, and for the turbulent you have them as empirical correlations, and we have got a hybrid expression and we have a constant value. So, the constant value is of course for a very large Reynolds number, so which means that for a very variety of industrial problems we can go ahead and use this assumption and solve some of the problems. So, we have now got the strategy, we have got the expressions, which means that we can now solve some numerical problems by using these expressions, which we will do it in tutorials as part of this MOOC. So, at this moment we will close this session, and the course website will contain the notes about some more details about these and also some numerical problems for you to practice.